Why? Because if you do not, your desktop or whatever directory your R Markdown is in will be filled with tons of stuff that you don't want. You want it, but you want it in a folder you know that makes sense. If you don't do this, it's not my fault. All right. So we're going to go. Let me get out. So a few things about these slides. We're going to be playing in the Markdown for the most part, but I generated slides. If there's a citation in the slides, it links to the paper, so you can click the citation and get to the paper. Why did I make slides? Because I'm trying to convey a workflow today where community detection and role analysis are central parts of that workflow. So in the Markdown, there's a big focus on what command does what and etc. But the slide should help you be reminded about why am I doing these things, and I'm going to try to do that in the Markdown. So you should have slides. You should have this Markdown. Now we're about to go into the Markdown. All right. Does everyone see a file? Let's go to the very top. Just quite a few commands at the top. Everyone see a file kind of like this? You have this on your machines? Yes? Yeah? Okay, good. Good. So we're going to go first to Renaissance Italy, and we're going to go look at the Florentine families network a little bit. And then we're going to go to the universe of Marvel. The Florentine families is a happy small data set, and we're going to do a move where we're first going to look at our network, examine it a little bit, then we're going to do some community detection to understand if there are underlying factions, underlying groups, and then we're going to do a role analysis to look at what are the sort of leading characters in our story. So, with further ado, okay, so I have this first. Let me go up here, make sure I don't go too fast for myself. Yeah, I've been playing around too much. All right. I probably don't need to hit knitr command. So just loading in my packages, not a big deal. I cleared my stuff. That was sad. I have this here. This is because I have all these files coming down this place. It's just to make sure the files go to where you want them to go. You could do what Leanne suggested earlier, which is set your directory by just hitting session that way. But this is like the guarantee that things are okay. Okay. And then so this is just a description about the Florentine families. It was collected by, so it was collected by a historian named Paget. And then it appeared in the networks literature. Breiger and Patterson had this really nice paper that featured the Florentine families in it. And the Florentine families consist of two networks. We're going to look at one of them today. One of them is marriage alliances. That's the one we're going to focus on. The other one was money and sort of trading networks. Okay? Just to give you a little bit of history. So I get down here. Let me go up. I go too fast. Okay, so we need to load this in, and we're going to get this from IdeaNet. It's actually part of the package. Oh, what did I do wrong? Oh, I went, like way down here. Okay, so you should see loading Florentine families. I am a newbie to R Markdown. I'm a complete rookie. So it's not my native thing, and I apologize. So we've got this data set in here, and NetWrite's actually done a lot of work for us. And so what we can now do, I just want you can do this in the console, or you can look at this. If you do summary, and at Florentine net, it'll tell you all the cool things that are in here. And then I'm just going to focus on one of them right now, which is if I do Florentine net and I do the system measures plot. Both plots are useful. And then I just hit enter. Oh, I did. So this is giving me a sense of the degree distribution. So, and it's giving me, okay, what's my assortivity, so my bunchiness in my network, what's the reciprocity rate. And then we can also, the global clustering coefficient, which says, well, we definitely have some clustering going on, but this isn't the tightest setting ever. We can also look at the system level measures. So we can do Florentine net. I'm doing this because it doesn't show in the markdown super well. So, and I can go node measure plot. And hopefully it shows up. And then this can give me a sense of like, all right, what is going on? First high level thing, what is going on in my network? So I can see my weighted degree distribution. So I have weighted ties, it's good to see. If I didn't, it wouldn't show up. I can get a sense of, okay, I definitely have a distribution of, there's people that are close and people that are far. I'm also kind of interested in betweenness. So while there's a lot of people that are kind of out here, I do have some highly people between lots of paths. I know that because I have this right skewed tail. So as you get more into network science, these plots mean more and more to you. I'm just sort of going, look, we're doing a first pass on our data, okay? So now we've got it in. NetWrite's giving me all sorts of diagnostics, of which I'm not going to exhaustively do them all. Now I'm going to plot the network. Now, why did I do the measures plot? And why did I do those things? Because I work in a setting often where I can't actually plot the whole network. Like, my computer would blow up, I'd be there all year. In Florentine families, things are nice. Even in Marvel, we can still sort of plot the network. So you could have been like, why didn't you just plot the network, John? Why did you do these other plots? Well, it's because if you're working in a large enough setting, because maybe you're working on like document networks or sort of these bigger settings, these things can help you. You basically begin falling back on 2D measures because the network visualization becomes intractable. So if we do, let's do that again. Okay, we've got our little network. And I did a few things here. There's a backstory to this network. Anyway. So there's blue Medicis, and then there is the Strozzi. The Strozzi were a family who tried to challenge the Medici supremacy in Florence. No one knows who they are now. And we're about to see why in just a minute from a network analytics sort of approach. Okay. So if we go down here, and I was sort of talking about, we're going to do our first clustering. So we're going to go, what are the factions? Because I've already sort of gone, there's a Strozzi faction, there's a Medici faction. Well, now we're going to use community detection to help find it. Because maybe you don't already have this backstory. Maybe you don't, maybe oftentimes I'm working in settings where I need to begin, I'm using community detection to begin to find those underlying factions. But I will also note that community detection is an art. And you're going to get a partition in a second here. That partition does not align with your domain area knowledge of the setting. Then either there's something going on with the data or there's something else. You don't ever ride your whole analysis on the results of a community detection or you will be sad. All right, so we're going to go this. And it didn't plot it. Why? Because I suppressed it for the purpose of the PDF. But let's bring it up here in a second. So I've done, I set all the plot elements. Okay. So I'm going to do the plot now. There's a ton of NetWrite stuff in here, which I'm going to talk about in a second that show up. But if I just copy and paste the plot statement for a second, just to be like, we've got a plot. Okay, so community detection, now we've got our families. We see the Medici in red here. I will say also these plots are stochastic. So if I was very high speed and I wanted to show this to many people, I would actually set this layout so I could more easily talk to it, but I wasn't high speed enough, so I didn't do that. But any event, we can begin to see these underlines, so the Strozzi's in a different color, Medicis. Okay, Now, NetWrite, so we've now gone, here's factions. Now we're going to go, who's important? And there are many, many ways to do that, and role analysis is one of them, and that's what we're going to do here. And I'm going to there are objects. So I'm going to go down here. IdeaNet helps us out with this. So I'm going to scroll down. And I can do this Florentine clusters object. And it's going to produce a lot of stuff. And frankly, I'm totally cribbing from Tom here. So that stuff is in your machine, I promise you, I swear to God. But this is much nicer displayed this way, and I kind of did a short version. So what did we do? What we just did is we said, okay, I'm taking this network and I'm generating a lot of features. I'm generating triadic closure features, the triadic census features that Jim was talking about. I'm generating degree features between this. I'm generating a bunch of characteristics about each of these nodes in this network. And then I am essentially using an algorithm to partition it and make a tree. And then I am optimizing on that tree to identify particular roles. And now why did I go to Tom's great work here is, okay, great, we identified roles. So these are all these characteristics. Tom already did this for me, so I'm just it's there. But anyway, so these are these characteristics. We've got mean total degree, mean weighted degree. We're looking at these marriage totals, and we can dive into that a little bit more. But we can also look down here, and we can begin to see across these measures, there's one position not like the others. And if you go scrolling down across these different measures, and particularly if you go just a little bit farther down, there's these nice betweenness, Bonsic. This particular one's very happy for my story. Somebody's in role 6. I wonder who that is. Well, let's go confirm that, right? So we can go back here and scroll down a little bit. So all those objects are made, but Tom did a much better job, so I just pointed that. So now we're plotting roles. This is them being plotted onto the network, and it's super small here. In the slides, it's not. The colors correspond to those positions, and particularly position 6 is that white position, that one with the high betweenness and brokering. And the thing is, you would definitely, if you were working with stakeholders, you need to educate them about this. You can't be like, oh, here's this role. So there is a little bit of what do these different things mean? Yeah, it sucks. Markdown, not my native language. Okay. All right, so I'm actually going to go back to the slides really quick because it's displayed a bit bigger and nicer there. That's then clustered, right? This is the dendrogram to describe the cuts. And then there's the meta cheese. And I've cheated. I sized it by betweenness because, when I saw the role positions, I was like, oh, good. And basically, the Strozzi were run out of town because the Medicis had a lock on Florence through their marriage alliances and brokering position, which is the sort of end of the story. But imagine I didn't know that history. These methods helped me sort of able to uncover those kinds of dynamics. Okay, so now we're going to go to another setting, one closer to things that I do quite a bit. So I work on large graphs, particularly social media data kinds of graphs in my day job. So if we go back down here, so this is introducing this setting. Well, I'll go to the slides quickly because they're fun. So we're now in the world of Marvel. All right, and now we've got a huge graph. You're going to look at this thing, it's like, it's terrible. It's huge. So what are the connections? So we have comic book characters, and they co-occur in comic books. And what I'm going to display for you is like, how do we break this network down to start building insights from this huge tangled mass of horribleness, right? So let us begin. So first of all, I've got to read in my data, okay, surprise, surprise. And I'm bringing in all these elements, which is why you made a directory, right? We go down here. Now we're just basically getting our network. And we're going to look at it a little bit. So do our first inspection. This network's just on the order of maybe not, this is not such a good idea, so I cheated and I did the layout ahead of time. So we're not doing 5 minutes of waiting for it to lay out. But we're going to do a little bit of an inspection. Oh, it's still taking longer. Okay. It's a mess. It's a big ball, right? So we're gonna unpack this ball. All right. Now, next thing we're gonna do is we're gonna look at the isolates. Yeah, 1 is the loneliest number, and it's sad. But in my setting, and it can be true for you too, you might have collected his data, and you might not actually have, the isolates might have been the people that you actually cared about, or there's 1 or 2 isolates. And then, so often in network data collection, it's somewhat iterative. So at least in the settings I work on, like, okay, who are the isolates? Is it okay that they're basically isolated? Or are there isolates that are sending a warning sign that maybe this network data isn't actually addressing the analysis question that I want, or other red flags? So it's just a data quality check. But we're going to go look really quick at our isolates. And, well, I'm not too worried about the letter A. And these aren't, Wolverine is not on this list. If Wolverine was on this list, I would be going back and I'd be going, what's going on with my data? I might have done something wrong. I might have brought it in incorrectly, whatever, right? This is just a data quality assurance check. But now we've confirmed, and you can look down further in the list. Now that we've confirmed that our isolates, it's okay, we can delete them with impunity and move on. And why are we doing that? Because in community detection, an isolate is a community. It's just a community of 1. And it's not particularly interesting in terms of, like as Jim said, there's not a lot of data about it. But you could get a community solution that's got like 500 communities because you've got like 400 isolates. So dropping isolates is an important pre-step. Now we're going to look at tie strength, because I have a weighted network. These are co-occurrences. And I want to get a sense. First of all, okay, so mean, standard deviation, median. So yes, I definitely have a little bit of a right skewed distribution. My mean is 1. That's sort of sad, only 1 co-occurrence. But I've got a pretty big standard deviation. So we're going to do a little bit of a visualization just to get a better sense of the weights. Okay. These weights say, why did I bring up the weights? Well, I want to chop the network down. I need to reduce it. But one common way to do that is a process called, it's colloquially called thinning. And there's 3 different general approaches. One of them is you do a threshold. And you're like, I'm cool with everything below X being out. I don't like doing that. I'm not going to do that in community detection talk because I want to preserve as much as I can the community structure of the network. And if I go across all those like 500 things, like a lot of community structures has gotten destroyed. The next good thing to do, that better thing to do, is you might be like, okay, I could actually look at if the ties occur more than we expected by chance by pulling some kind of chi-square framework in and go, all right, look, ties that aren't expected greater than chance, I could drop those. We're going to do a thing called rank tie thinning, which is the third option. And it's because it's particularly robust on really big graphs. But we're going to say this K, we're going to keep all the tie. Every node gets to stay. And we're going to take K number of ties. So like basically, I believe our K in this network is 25. Each node, we keep your top 25 connections in terms of weight. And the rest drop. This tends to keep the backbone of the network, but thin out the network to make it a little bit more manageable. So there's functions that you just download or they're available to you. We're just going to run this really quick to thin this. This is, I think, the thing that takes the longest in this whole presentation. So it won't take too long, but any event. So this is, yes? Why do I want to thin the network?
So is that like you might take the top X many per node versus
Yeah. Yep, that's sometimes called an island approach. The idea is you've got the sea and you're taking everything above sea level. That's a approach. And so if you're like, look, you know, what I care about is the people that have lots of connections, that's okay. Like, there are substantively different choices for different points. But because I'm doing a community detection talk, I really want to keep the community structure as much as I can, which is why I'm doing this rank approach instead. But there are other places where that would be, you know, great. But the idea is we're trying to manage this unwieldy network. Let me check time. All right, we're okay. Wow, 4:13. Scary. There'll be tons of time. Okay. There was an hour. It said, oh, well, that's fine. I can make it by 4:30. I'm good. That's okay. So now we're going to cluster it. Oh, wait, I'm way up here. Sorry. I got lost. We'll get down here. Sorry. Apologize. Boom, boom, boom. Yeah, okay. Not that far down. So we inspected the network visually. We've looked at the isolates. We've done this. Yes. Right. Thank you. I just don't want to do the thinning again. So, did I just do the thinning again? I did the thinning again. Damn it. All right. Well, does anyone, while this is doing this, anyone have like sort of general substantive questions? Because I'm going very fast, I know.
It might be worthwhile just pointing out that the logic of thinning is that these really big, dense one-mode projection networks can often, effectively, a lot of really weak ties will swamp the signal from a smaller number of strong ties. And usually what you want to know with community detection or something like this, or a lot of times fusion, is turning on the structure imposed by the strong ties and let the weak ties follow. So that's the substantive question. So you could run this model without any thinning at all. It's just that the story you get is going to be swamped by the characters, in this case, that appear in the comic book stories 1.
Okay. So we can check. We have managed to reduce these ties. We have this network. We do a little bit more of an inspection. It was to check that our thinning did not do undue violence to our graph. But now we're going to look at the thin network. Okay, it's still a mess. So now we get to do the fun part, which is we get to cluster it. So first thing we're going to do is we're going to cheat. We're going to get the largest component because there's 4 components. There's one that's thousands of nodes. And then the next one's like 30, and there's like 4. And then there's like 2 or something like that. So we're focused right now on the largest connected component. And now we're going to perform community detection round 1. And that's just performing it. Oh, yeah, so did I suppress stuff? No, it's okay. Let me go down here. And then, yes, so we can go look at community memberships. So this is just getting us a sense of, okay, who's in our communities. With more time, we would do sort of a deeper dive. But we can go look at the counts of the communities. So this is now looking at the sizes. And you could do something like look over at your data frame, for instance, and begin to get a sense of what's what. And then let's go down here. And we're going to, this is, again, looking at these weights. Or actually, this is sizes. So this is looking at this variation in sizes of our communities. And so we've got some really large ones, and we have things at 15, but not like 10, 15, but not, for the most part, we got some fairly large networks. We're going to shrink it now. So what this is doing is we're going to make a community-to-community graph to get a sense of what are the connections between the different communities that we made. And that can give us some intuitions about this graph. So, okay, we've got around 30 communities. Yes, we have a dense core, and then we have some communities a little bit farther out. But we still don't know, like, who's in these communities exactly. Like, how do we actually begin to unpack what communities matter? So what we can do is, this is a lot of talking about it, we're going to go look at the agents that have the highest in-group degree. So who is most connected within the community? If you did total degree, that would be most connected in the whole graph. So what we're doing is we're taking a graph, we're extracting out the between group ties, and we're calculating degree on just the in-group ties. And then we go down here. And we should see, let's just run this quick. All right, so now we've got, this table is ranked by the largest communities, is ranked by size. We have the top connected degree. Looking at this, does this make sense? Knowing what you know about Marvel. I mean, you guys how many movies have we seen, right? Yes, come on, yeah. Okay, good. So this is again, sort of a descriptive trick, like, hey, is what I'm doing make sense? I would expect that Wolverine or Iron Man is at the top. If my highest communities, if I'm getting like the letter A, which I had a version of this where I did, that would be indicating a bug. That would be either there's like something going on in the data or some data processing thing. But this also can be used to begin to label the node. So people know Wolverine, and they know that that's indicative of the X-Men. But hey, let's not just depend on the largest community, or like these sort of community summaries. We can also, and I'm going to go through this quick for the purpose of time, we can also extract the communities. So these are the 4 largest communities. So we've got the X-Men over here. We've got Iron Man over here. If I was really high speed, I would have actually labeled them by these top people. And then we've got, this is, I think, Doctor Strange, or that's Doctor Strange. And then let me go up. Who is community 6? Up at our table. I went too far. Let me go to the slide. Let me go to that here. Boom, 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 boom. Yeah, there's a lot more in the slides, but yes. So, right, Spider-Man. Forgot Spider-Man. Oh, goodness. So, with being able to extract these out, then, and let's go down here really quick. The next step would be you can do this again at a smaller scale. Now we have so one interesting thing, look at the X-Men. It's like, I think Wolverine and a few of his compatriots are basically like hoarding the whole story. You've got this like super core periphery network for the X-Men, whereas you're looking at Iron Man. If you know anything about comics, Iron Man showed up like with everybody in the 60s. Iron Man is not actually super surprising. But you would then begin to you can see clustering within these clusters, and then you can begin to detect what are the subclusters within there. And then it just goes on and on from there. But these are ways of simplifying a really large mess and doing checks along the way to see, am I making sense of this data? And if anyone has questions about what I did or why I did it, please follow up with me after the session. And it's 4:15. I could give back some time. Is that okay? All right. It's been a pleasure. Thank you very much.